Hello, everyone, and welcome. Thank you all for joining us for today's session. My name is Firas, and I'm the event planner for the Microsoft Reactor in Redmond. Before we start, I have a few things to go over. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our presenters and audience. We encourage engagement in the chat, but please be mindful of your commentary and please remain professional and on topic. This session is recorded. It'll be available through the Microsoft Reactor YouTube channel in about 24 to 48 hours. I'll be sharing the link to the YouTube channel in the chat. I'll also be sharing some links for the Reactor meetup page, as well as a link for the survey to know your feedback as well. Which brings us to our session today. This session will run approximately for 1 hour with time for questions within. Our speaker for today is Jim Bennett. He is a regional cloud advocate. I'm now going to pass this for Jim.
Awesome. Thank you very much, Firas. And hey, everyone. Welcome to this session, wherever you are in the world. Good morning, good afternoon, good evening. Thank you for joining me for another Jim Learns Stuff. So for those who don't know me, I'm Jim Bennett. I work for Microsoft. It's my job to do cool things like this stream. And if you want to get in touch after today's session, if you've got any questions about anything we cover or just want to hang out, get in touch with me. I'm all over the internet at Jim Bob Bennett on Twitter, GitHub, Instagram, LinkedIn. Feel free to reach out and connect. Now, today's session is all about ancient cryptography. Now, this was actually inspired. I was doing a stream a while ago, got challenged to, we even got talking about this book I've got, which is called Decipher, which is all about cryptography. I'm just got talking about ancient cryptography. And it was suggested by someone that I actually do a session and we kind of dive into some ancient cryptography using Python. So that's what today is all about. We're going to talk about some of the classic ways in which people hid messages. And we're actually write some Python code together to do some encryption, decryption, and then even look at how we can try and crack some ancient cryptography. So should be a bit of fun over the next hour. So let's, I guess, kick off with what is cryptography? You know, people talk about cryptography. What is it? Well, cryptography is the art of concealing communications. It's taking some form of data, a message, and then turning it into a form that you don't know what it is, and then only the intended recipient can actually then decrypt that and see what the other side is. So I could take a message that I want to send to you, I could encrypt it. That way, if anyone else got hold of the message, it would just appear to be garbage. But then when you receive it, you can decrypt it so you can actually understand the content. Now, cryptography has been used for thousands upon thousands of years. I mean, in modern times, we do it all the time. I mean, right now, you are all watching this over HTTPS, which is secure HTTP, and that is encrypted. So we use it now for encrypting our web traffic, so people can't see what it is we're looking at or intercept that or change that. We use it for securing messages. If you use platforms like Apple's iMessage or WhatsApp, your messages are secured. Only the sender recipient can actually read them. If anyone else intercepts it, it's just garbage they can't use. And we use it for securing business data. You know, when we save stuff from the cloud, it's all secured, it's all encrypted. And we use it for, you know, storing the data from your computer. You know, your hard disk might be encrypted. So it's kind of big, it's everywhere. But say it's been around for thousands upon thousands of years. So today is all about winding back the clock a few thousand years and actually learning a bit about the history of it and having a bit of a play in Python. And Just For You says, hello from Baltimore. Hello, Just For You. Welcome. Welcome to the stream. Hope this is going to be a fun one. So I guess I want to start with a question for everybody is, has anybody ever done any kind of simple cryptography? And by that, I mean, have you ever swapped letters around to send messages to your friends? You know, you may have done this back in even elementary school or middle school, you may have done this. But if anyone's done anything playing with kind of cryptography, let me know. I want to hear. Let's have a chat about it. So let's kind of dive in to, not that one. Pressing the wrong buttons here. Let's actually dive into the earliest known cryptography. So this is where we go right the way back. Now, Marcy says, yeah, lots as a kid. Yes, a lot of kids do this. They want to exchange messages with their friends, so they kind of encrypt it by just swapping out some of the letters or coming up with their own secret codes, even secret languages. Rory says, indeed, yep, same thing, just way of sharing messages. Cool. It's great to know that some folks would do this. I used to do it as a kid. Used to do it a lot as a kid. My daughter's been doing it in school. It's great fun. So the earliest known possible encryption, let's say, may have been around for earlier. The earliest that we know about was actually from a tomb in the Old Kingdom of Egypt, where some non-standard hieroglyphs were carved into a whole load of walls. And this was back in 1900 BCE. So we're talking 4,000 years ago. And nobody really knows whether it was encrypted messages or whether it was just somebody just mucking about and just basically trolling any future grave diggers. But they actually had non-standard hieroglyphs. So rather than use the standard hieroglyphs of the time to write the messages on the walls, they used non-standard ones. Could have been some kind of secret code. Don't really know. But certainly at around that time, cryptography was starting to form. People starting to get ideas. And there was found a clay tablet found in Mesopotamia in the Middle East, 1500 BCE. So we're looking at 3,500 years ago, that had an encrypted recipe for a pottery glaze. So craftsmen got these amazing pottery glazes and actually encrypted their recipe on a clay tablet 3,500 years ago. So it's pretty cool. It's a big thing that was forming back then. And you go back to kind of 600, 500 BCE, Hebrew scholars used very simple ciphers to kind of share data. So it's got a nice long history. Now, one of my favorite early ciphers, and I absolutely love this one. This is quite a simple one that we're gonna look at today. Was from a classic Indian text by the Brahmin scholar, and I'm probably going to pronounce the name wrong. We're going to do my best here. Vatsyayana. So if anybody actually knows the correct pronunciation, Vatsyayana, please let me know. But this was a text written in the 4th century CE, but it's based off writings from 800 years previously. It's a classic Indian text. I'm not going to mention the name of it because, unfortunately, the name of it has got some different connotations in the modern world. It's a classic Indian text, and it had some very outdated views. One of which was that women should study 64 different arts. Okay, so the 64 different arts that women should study included cooking, dressing, massage, preparation of perfumes, conjuring, chess, bookbinding, and carpentry. So, Vatsyayana was obviously very keen on women having a very well-rounded education. Obviously, these are very outdated views. But one of the things on the list was Mlechita Vikalpa. And again, I'm probably pronounced this wrong, but Mlechita Vikalpa is the art of understanding writing in cipher and the writing of words in a peculiar way. And so he actually recommended that women learnt how to encrypt messages. And he suggested something that lovers should use to exchange love notes. So if two people fell in love and maybe their families didn't approve, they could exchange love notes in that were encrypted, or even they just wanted a bit of privacy. You think now when I send a message to my partner, I do it on an encrypted texting app. Same kind of thing. It was allowing people to send love notes to each other, or even to document their romantic liaisons without family actually be able to read what they've been getting up to. So really kind of nice. I love the fact that it started with people sharing love notes to each other. I think that's really cool. And this particular cipher for doing this was a thing called a substitution cipher. So substitution cipher, the whole point of substitution cipher is you take letters and then you substitute them for another letter. So one classic example is where you kind of fold the alphabet around. So if you have your alphabet here, A to Z, kind of fold it around and you substitute A with Z, B with Y, and so on. M with N, and then N with M, and then Q with J, and W with D. So you kind of swap the letters around, and then you take what you've written, You then swap all the letters for their substitution and then give that substituted form to your lover. And they could then decode your message of love and then write back to you again, substituting the letters. It's a whole different variant of how you could do this. Kind of folding the alphabet in half is one way to do it, loads of different ones. So example here, if I wanted to encrypt hello world, for H, we do S. For E, we do V. And so on and so on and so on. So hello world becomes Svul Dlo. Svul Dlo. So I would send this message and the person on the other end would then decode that same thing. S is H, V is E, O is L, O is L, L is O, hello, and so on and so on and so on, and decrypt it. Nice and simple. But if you don't know that this is how it's encrypted, you've got no idea what this could be. Especially going back, thousands of years, this wasn't a regular thing people did. This could be in a foreign language. You've got no idea what this is. Now, obviously, this is a simple, you fold the alphabet in half, but there's so many other things you could do. For example, if you both have one book that you love, it's got a book that you love, you could say this book is the Substitution Cipher, and you would find the first occurrence of an A in the book. So the first occurrence of the A in this book is the word A, the next letter is H. So I substitute A for H. First occurrence of B is the word book, B-O. So substitute B for something like that. So you always have some kind of agreed way of substituting the letters. And as long as the sender and the recipient know that way, they could do it. Now, actually, ancient Sparta, they had quite a cool kind of twist on this a little bit. So they decided to shift their alphabets a bit and come up with weird things using paper. I thought this was pretty cool. So ancient Sparta used to use a thing called a skytail. It's a rod of paper, and you wrap a piece of paper. So it's a wooden rod. You'd wrap paper around it. And then where the paper's wrapped around it, you could then use that to either guide the substitution, or you just literally write the letters on the piece of paper. And then the only way you can decode is if you have a rod the right size. Either the rod the right size allows you to wrap it around and read it off, or the rod the right size allows you to find the substitution. So it's kind of a bit of fun. So I've got a challenge for you, actually. This is a challenge I've got for everyone here. Just using this substitution cipher where we fold the alphabet in half, I'm actually gonna drop some text in the chat. This is a link. If I can actually get it to copy, I'm gonna send a comment with a link there. You have to decode this. So this is your challenge for either now or later. You need to decode this using a substitution cipher. This one here, and then see what that link points to. So that's like a little challenge for everybody to try and do throughout today. So that's a substitution cipher. You literally swap letters one for the other. Should we code it in Python? Should we actually fire up some Python and actually write some code? I think we should. And these are quite nice as kind of good little Python exercises. You think people doing kind of leak code and other kind of exercises as part of trying to get a job, for example. These kind of things can be a little bit of fun to do. So let's actually build a substitution cipher in Python. So here I am. I'm in Visual Studio Code. I've got the Pylance extension installed, so I can actually do all the various Pythonic things and get all my IntelliSense and all that in VS Code, writing Python. And I'm going to build a substitution cipher. So I start by defining the alphabet. So I've got my alphabet, my A to Z. And then when I substitute, I use the reverse. So as we had on our thing here, we use the reverse. So A goes to Z and so on. So I literally take my array of letters and I reverse it. So it's quite nice. I can just literally convert a string to a list. It becomes a list of characters. And then I can just reverse that. And then I can zip the two up. And this gives me a nice dictionary of the letter from substitution alphabet, the letter from the alphabet. So I get Z goes to A, Y goes to B, and so on and so on and so on. I can use my dictionary as my little mapping between the two. And then after that, I can just ask for phrase, what I want to encrypt, ask for that, and then I can start encrypting it. So just define a little function here, substitutes. So this will take our map, our substitutions of one letter to another. It'll take that, and then if the letter's in our dictionary, if it's a letter that we want to process, we literally look up the corresponding letter and return that. And then I can just use a little join statement. There was a map statement on here. Loka managed to decode it and just got rickrolled. Yes. Nice. Yeah, I couldn't resist the chance of rickrolling people. So good job decoding it. Glad you got rickrolled. Nice. Did anyone else get rickrolled? We're interested whether anyone else managed to decode it. Yeah, sorry, I couldn't resist that. I couldn't resist rickrolling. Cool. Finally print out the results. So come trace its London code. We've got our alphabet, got our substitution, which is our reverse. And really, I can make the substitution kind of be any. Loka says that was fun. Yep. Glad you enjoyed it. I just thought that'd be a bit of a fun thing to do. We've got our mapping. You know what? Let's actually print this out so you can kind of see what I mean. Let's just do this. When I run this, this is our mapping. Z is mapped to A, Y is mapped to B, and so on, all through my alphabet. So I can now just use this to do my lookups. And then whatever thing I take, I can just swap them over. They're just swapped over. So I can encrypt and decrypt the same way. That's what's nice about this kind of alphabet to reversed alphabet format. Encryption is the reverse of decryption, which is pretty cool. So if I just uncomment this, and if I run this code again, enter phrase to encrypt or decrypt, hello world, and we get our svul delay. So we can put anything in here, and it'll just literally just substitute it around. And because one has reversed the other, I can swap my mapping round, still get exactly the same answer. So it's kind of nice. I can encrypt and decrypt. If I now run the same thing and then put in my inverted phrase, Sordillo, hello world. So, if I could share this Python code with my daughter, for example, and I could send her secret messages just for a bit of fun. Just literally run the same code. Encrypted messages goes in, decrypted one comes out, or the decrypted one goes in, encrypted one runs out. So these ciphers weren't that complex if you knew what the cipher was. This is kind of it's part of this idea of security by obscurity. It's not that difficult, really. As soon as you know how the cipher works, it's trivial to crack it. But if you don't know that it's encrypted in this way, then you can't do it. This is not bad for 2,500 years ago as a way for lovers to exchange messages. It's very cool. So moving on a bit further forward in time to Julius Caesar. This is kind of the next cipher is from Julius Caesar. So has anyone heard of the Caesar cipher? It's kind of one of the most famous ones. But the Caesar cipher, a question, yeah. Alejandro, yes, please, ask a question. Where can we access the code? Yeah, that's a great question. Let me just rearrange my windows a bit. Let me rearrange my windows a bit. They're all going all over the place. I do have all the code on GitHub. I was going to share the link later, but you know what? Let me just grab the code. now. So just get a short link created for you. So yeah, in a second we'll get that published. Hey, no worries, no worries. So all the code that I've been showing today, it'll all be there. The encryption, decryption, the Vatiana cipher, the Caesar cipher, and then all the stuff I'll be showing later to try and crack it. That's all in that GitHub repo. So we'll just get a short link created, so you don't have the horrible long GitHub thing that kind of fills up half of the link. So yeah, we'll get that pasted in the chat fairly soon. Cool. But yeah, always ask questions. These kind of live streams are designed to be like a conversation, so you can just chip in with questions at absolutely any time. Yeah, no, it's cool. We'll get that shared. So yes, Caesar cipher. You may have heard of Julius Caesar, kind of a famous dude. Became the dictator for life of Rome. Not actually an emperor. A lot of people thought he was an emperor, but the term Caesar became synonymous with emperor. But yeah, it's I guess not his descendants, because it was great nephew that took over afterwards. But yeah, the future rulers of Rome took the term emperor, but he was just dictator for life. And he used ciphers. He was a big use of ciphers, and he used what's called a rotation cipher or a shift cipher, which is similar to a substitution cipher, but it's designed where the letters are shifted. So unlike substitution, where the substitution could be anything, the Caesar cipher is all based off shifting text. So he used to use a shift of 3, a left shift of 3 in all his text. So what you do is you'd line up the alphabet like this, and then you would shift by 3. And then that's how you'd substitute. And it will wrap around the end. So D becomes A, E becomes B, and so on. Z becomes W, and then it will wrap round. So A becomes X, B becomes Y, and C becomes Z. And you can have this wrapping round either way. It doesn't matter which way round you want to do it. You could wrap it round as long as you know and the recipient knows which way it's going to wrap. You've got this encryption. And so say Caesar used to use 3 to do this. So if he's doing hello world, you'd have, so H is E, E is B, you have Ebil Tloya. Ebil Tloya. So same idea, substitution cipher, all just based off that rotation. And he used this for all his correspondence during his campaign in Gaul, where he went around killing people who weren't Romans. He used this to communicate with generals and write letters to his friends, things like that. So really great cipher if you don't know what it is, especially if you are going around killing people in lots of different countries, because you're going to be exposed to lots of languages and nobody knows what the language is. This could be encrypted, or it could just be in a foreign language. So again, at the time, but yeah, we're looking 2,000 years ago. So this is quite an effective cipher at the time. So we can actually do that. We can knock a bit of code for that. So let's just delete this and start all over again. So start by getting the phrase that we want to encrypt, and then how much you want to shift it. Say Caesar used to use 3. Shift letters 3. Okay, cool. Alejandro, the link's in the chat. It hasn't been short linked. It's just the full GitHub links in the chat there for you. So that's all the code. And then with this cipher, it's a shift cipher. You have to shift the letters. And the way we can do that, it's pretty cool, is using the fact that the way computers store letters is using numbers, essentially. Computers just use numbers. So when we store a letter, going back a long time, letters were always stored using something called ASCII. So ASCII would be a number from 0 to 255, and those numbers map to letters. So when you store hello world, you store the H as a number, E as a number, L as a number, and so on. We still do that now. We do that using Unicode, which allows us to include more than 256 characters, because you've got emojis, you've got non-Latin alphabets, the whole lot. But ASCII basically gives you the numerical. You can always get numerical representation of a letter. And the way letters are stored in ASCII is always in alphabetical order. So whatever is the ordinal of A, whatever the number is used to store A, one number higher is always B. So if I just go, for example, Python here, and I go print ord A, that's 97. If I do B, 98. And obviously C, as you can guess, 99. So because it's stored as a number, we can rotate it by looking at the number of the letter and just adding 3 to it, taking away 3, kind of do whatever we want to it to kind of shift it. And that's once we've done that, we can then do a little bit of wrapping code so that if we go too high, we can wrap it round. So for example, if I look at Z, that's 122. If I want to shift Z, I mean, 123 is not, there is no letter after Z. We just need to make sure that we wrap it back round. So we convert our letter to its ASCII number, its numerical representation. And then if it's not a letter, we just leave it as it is. Because, if we want to put things like commas and spaces, we don't want to encrypt those. We then shift it by the amount we want to do, shift that number. So A is 97. If we shift it by 3, that becomes 100. Z is 122. If it's -3, it becomes 119. And then we just do some wraparound. If we go past Z, we do some wraparound. This wraparound is the idea that when we go past here, we have to wrap round. And so we've got a bit of code there to wrap that. And then just return it. It gives a nice little function here to shift each letter one by one. Then we can take the phrase that we want and just map every letter in it through our shift function to give us the shifted value. And then we just print this one out. So again, it's like 36 lines of code. If I run this, enter phrase to decrypt or encrypt, hello world. Let's shift it -3, and we get Ibil Flyer. So that's our nice encrypted phrase. We want to decrypt it. Decryption is the reverse of encryption. So we'll do the same thing. We encrypt that, but instead of doing -3, we do it 3. This is hello world. So we can kind of go back and forth as long as we know that number. If we tried to do the same thing, but we thought that it was shifted by, say, -7, so we need to shift it back 7, we get lips asvba. So, you still have to know what that number is. Now, the downside to this is this one's actually quite easy to crack. Because if you know that it's been rotated, then you can keep trying. So we can say, we do it builds a lawyer 1. That doesn't make any sense. Do it again, 2. That doesn't make any sense. Do it again, 3. Hello world. That makes sense. And so we can decrypt it. Just literally, it takes us 26 attempts to decrypt it. So we can decrypt anything in 26 attempts, essentially. Now, this is kind of brings up one of the interesting things about cracking encryption, kind of decrypting things, is you need to be able to know what the right answer is. So I can tell that 3 is the right answer because it's in English, and I know that is not English. Is not English. Hello world is English. So I can actually use just the fact I know how to detect correctly decrypted stuff to actually help me do this. If I can read it in plain English, then I know I've successfully cracked the encryption. It's kind of one of the hard things, though. If you don't know what you're looking for, you don't necessarily know whether you've decrypted it correctly. Alejandro asks, how are spaces treated? Yep, great question. So what I'm doing in all my code is I'm just checking whether I'm a letter. So when my letter comes in, if we're not in the A to Z, if we're not from 97 to 122, then I just return it as is. So spaces come through as is. Earlier when I shared that link, you'll notice I still had the dot and the slash unchanged, so I didn't change those. But yeah, certainly you could expand on this, and you could say you could even do punctuation or spaces. You could encrypt those. You could always set spaces to be something different. So there's many things you can do there. But now here I'm just doing the letters A to Z, ignoring absolutely everything else. So cool. That's a Caesar cipher. So we've looked at a couple of substitution ciphers. We've looked at the how it was done originally in the I'm terrible with this name and pronouncing it, Vatsyayana cipher, using just simple substitution, and then Caesar cipher with rotation. And this is kind of the two classic ancient ways of doing encryption. And this kind of stuff, those folks who said they did it when they were at school, Marcy and Rory, probably this is the kind of thing you were doing. You were just doing simple rotations and substitutions. So we spent the first half of the session talking about encrypting. Let's talk about cracking that encryption. Now, I mentioned obviously this is a hard problem because you need to kind of know what the end goal is, what you're trying to get out, such as in, we're trying to get out in English. But how do we crack encryption? And obviously, I'm not talking about kind of what we do for encrypting web traffic. I'm not going to teach you how to be a hacker. I'm just talking about how do we crack this kind of ancient cryptography from thousands of years ago. Gnarly Duck says, good evening from Florida. Hey, Gnarly Duck, welcome. How are you doing today? Glad to have you with us. If you just joined, you've joined just at the right time to crack some ancient cryptography. So let's talk about decrypting. And this is the fun stuff. And the whole art of decrypting things is called cryptanalysis, which is pretty cool. And a lot of it was started by this person, Al Kindy. So Al Kindy lived in Baghdad back in 800, from about 800 to 873. He lived in Baghdad, and he worked out of the House of Wisdom, also known as the Great Library of Baghdad. This was destroyed in 1258, I think it was, by a Mongol invasion. The grandson of Genghis Khan just rocked up and just trashed the place, which is a bit mean, really. Lots of great learning happening there. But Al-Kindi was an Arab Muslim philosopher. And he was a polymath, mathematician, physician, music theorist, and he was one of the first of the Islamic peripatetic philosophers. I've no idea what that means. But no, he was known as the father of Arab philosophy. So one of the kind of first founding members of Arab philosophy. And this guy wrote a lot of stuff. He wasn't just into code breaking. He wrote treatises on metaphysics, ethics, logic, psychology, medicine, pharmacology, mathematics, astronomy, astrology, optics, perfume, swords, jewels, glass, dyes, zoology, tides, mirrors, meteorology, and earthquakes. So this is somebody who's definitely into some of everything. And he spent a lot of time just learning, studying, and coming up with kind of good works for the day. This is, as I said, 1200 odd years ago. A lot of great stuff at the time. And he got into cryptanalysis, and he actually wrote a manuscript called Deciphering Cryptographic Messages, which used a trick called frequency analysis to actually try and decode text. This is kind of a really, really cool idea, actually. So if you've ever played Scrabble, anyone here has played Scrabble, and you've wondered why you get different amounts of the different letters, frequency analysis is the answer. So when you look at a book, so here's like a book in English, for example, you don't have equal numbers of all the different letters. So if I just pick a page here I'm going to get more. If I look through this, it's going to take me a while to see a Q. I mean, this mentions Iraq, so there's one Q there. But I'm only going to get one Q all the way through this. I'm getting lots of E's, S's and P's and A's, only one Q. And this is kind of the idea that Kindy had, is that there's certain letters that are a lot more popular than others. And so if you can look at the general popularity of letters across the conversations, written texts, word usage, and then map that distribution to the distribution of letters in the text you're trying to decode, you can start picking out letters. And then from there, you can use that to kind of guide how you find more letters and slowly work out the substitution that was used. So, for example, this is a distribution of letters in English. So you'll notice E, 13%. So 13% of all letters across English texts is the letter E. Q, on the other hand, 0.095%. Z, 0.074%. And so if you've got enough text, it doesn't work for hello world, but if you've got enough text and it's all using the same substitution cipher, whatever letter appears the most in your encrypted text is probably the letter E. Whatever letter appears next is probably T, and so on and so on and so on. So you can kind of get quite a rough idea of the letters that you've got and then start to chip away at that, look for patterns and kind of solve it. You can do it with individual letters. You also do it with digraphs. So digraphs are letter pairs. The most popular digraph in English is TH. And so if you've got letters that you've always got the same pair of letters in a lot of different places, those letters are probably the most frequent pair of those is probably TH. So again, you can start making these more guesses against what's there. So let's do it. Let's actually do it. Let's take this text here, this whole big board of text here, and let's see if we can decode this text and work out what cipher was used. And so let me start grabbing some code. So the first thing I want to grab is all of that text. This is our big wall of text that we need to decode. So do it and then just print it out. So if I just run this, we just get, here's our big wall of text. Okay. Then I'm going to take Hill Tribe. Is that a big brain? Or is that an alien? It's a great little emoji there from Hill Tribe, and I'm trying to work out. That looks like a big brain. Yes, it's quite cool stuff actually. It's kind of an obvious realization when you think about it, but it is making that mental leap of, oh wow, Hill Tribe G confirms, big brain. Making that mental leap of, yes, if it's the most popular letter in English, it's the most popular letter in the encrypted text must be E. So it's impressive stuff. We define our letter frequencies. A is 8.2%, E is 13%, so on and so on and so on. This is our different frequencies of our letters. And then we can actually count the letters in our encrypted phrase. So what I'm doing, I've got a bit of code here that goes through and builds up a dictionary of all my ASCII letters. So there's a string package, a string module in Python that's got things like all the lowercase letters, uppercase letters, things like that. It's quite cool. So I'm just creating a list of all the lowercase letters at 0. So a dictionary of letter to count of 0. And then I just go through my text and just count them all up. So that runs through, and this gives me the actual count of letters that I've got. Okay. And then once I've got my counts, I can take my first guess. So I can take all my letter frequencies and sort those in order. So most popular letter at the top, least popular letter at the bottom. So we start at E, go down to Z. I do the same with all the letters in my encrypted phrase. sort those out, and then I can just zip them together and make a very simple assumption that based off the frequency of letters, what that letter is. And then I can print out a mapping between those. So if I just run this, it is guessing as a first guess based purely on the frequency. The letter V in my encrypted text is the letter E. So it sees there's a lot more V's in here. So that is probably E. And the letter G is the next most frequent letter. It's probably T. Letter Z is probably A. All just based on those frequencies. So no guarantee it's correct, but it's just a good first guess. And then what I can do is I can use this to try decrypting it. And so I just use this mapping that I've got, and then I just go through, essentially running a substitution cipher using my mapping and spits it out. So if I run this, what we've got is still nonsense. Tree ilhe and the sogs fini ob. So it's still nonsense. So we know that it's definitely not a one-to-one mapping. But we can then start looking at things we can take a guess about. You know, this is where kind of we do have to get a bit of human involvement here. Not always easy to fully automate. So I've got here E.Y. Now E.Y. it's probably E.G. isn't it? It's probably E.G. Exemplia gratis, for example. So that's probably E.G. And if I look at my O.L. Where's the O.L. Basic. Sorry, Lopta, I'm not getting you. Oh, having BBC flashbacks. Yeah, all this stuff. Yeah, I used to write. I haven't written this decryption, but I used to write encryption programs in Spectrum Basic, which is pretty cool. So yeah, so we can make a guess that this E.Y. is probably E.G, because if I look where Y is, down here, it maps D to G and T to Y. In the original, that E.G. was V.T. And it mapped T to Y based on the frequency, but also G is quite close, isn't it? G is close in terms of frequency. We know E.G. is a valid expression, so it's probably going to be G. So we can say that yes, V definitely maps to E, T probably doesn't map to Y, it probably maps to G. And so what I can do is I can start building up a dictionary of mappings. And so if I just change that to this, I can define some known mappings. So I say I know that V, we've got the VT, that is EG. So V is E, T is G. I know that. And then I use those. Once I've mapped those, delete them from my frequency list and then map that again. So if I now run that, we've now got E.G. Okay, so we know 2 letters. We're slowly chipping away. We've got 2 letters. Yay! Only 24 left to go. But this is kind of the bit we can bring in more of our kind of human intuition. So the next thing we can do is just a quick one would be digraphs. So what I can do is I'm just going to drop in a quick bit of code right back at the start to find my digraphs. Digraphs are letter pairs. This is where anything, this is the letter pairs we're looking for. So the most popular letter pair in the English language is TH. So what we can do, we can go through the text, and then if we've got 2 letters in a row, so we use the is alpha on the string to say it's a letter. So 2 letters in a row, we then put those 2 letters in dictionary and count them. So if we've got like OI here would go in, but I space wouldn't go in. We use this to count the digraphs. We can use this to find the most popular and maybe make a guess that that is TH. So if I just run this, now here are my digraphs, big long dictionary digraphs. And the two most popular are SV and GS. SV at 36, GS at 31. So one of those is probably TH. Now we've already established that what do we already know? So we know that V is E, we know T is G. So is SV going to be TH or is GS going to be TH? So we can kind of make some guesses on this. So one of these is going to be, now they've both got an S in there, so SV and GS. So if SV is TH, then GS is something T. Is that popular? Don't know. If GS is TH, then V we know is E. So V is E, so that's got to be E. So that means this can't be TH, so this must be TH. G is T, S is H, and then we know that that could be he, because we know that. So kind of, you know, we know what V is, can't be this one, got to be GS. So we can say, well, that means G always maps to T, and then S always maps to H. We're starting to build up more of our mappings just using those digraphs. So if I now run all this through again, we're kind of getting closer. So now we've got, the ailerons, theen. So we've got a few the sounds, the. Yeah, lots of the in here. So that's probably right. So again, because we know it's English, we can recognize those English bits and pieces as we go through. It's pretty cool. And then we can just kind of carry on from here. So what have we got? What in here looks like it's right? What we spot English words. Here's one, tattoo. So we know that T is mapped correctly. And so tattoo reads right. Can't think of any other word that the A and the O, we have something else there. Something, yeah, I can, in terms of the English language, the only word I can think of where you have T, something, TT, something that's repeated. So we can use this again. So that one there, tattoo, is GZGGLL. This was the original one. So we can then say Z is A and L is O. Z, A, L is O. Again, slowly chipping away. Slowly chipping away. So we know that for sure. Now let's make some more guesses. So what can we guess at next? Thene. Thene is an interesting one. THENE. We know T is right, H is right, E is right. So this is going to be there or these. Could be one or the other. Could be there, could be these. So if we look at R and S in our letter mappings. So I mean, thene, if I actually look for it in the original, thene is GSVHV. So it's what is H mapped to? H, so H is mapped to N, and the S and R, so, and S is pretty close in our frequency mapping. So it's H is mapped to N, M is mapped to S. Pretty close in our frequency mapping. So if it's thinking N, it could be S. So these sounds like a plausible, it's a relevant word. So let's just try that. And yeah, just slowly chipping away. Now we've got better. Die Eilrest fürs Obdictorische Respoffen. Yeah, we're getting there. It's a bit more English sounding. Very, maybe heavily slurring. But we are starting to chip away, getting closer. What else we do? Let's look for some more English words. So we know about TH. Here's this one. Thoft. We know T is right, H is right, O is right, G is right, H is T. So thoft, that's going to have to be thought. There's no other letter I think I could put in that in the middle there. So it's going to be thought. So that one there, currently F is mapped to W. If I actually look at the original for that word, it is it that word there? Where are we? 1, 2, 3, 4 words in. 1, 2. Oh, glyph. Let me clear my, let me just get rid of some of the stuff I'm printing to make it easier for me to see. Don't you see the digraphs? So this one at Thoft maps to so much little stuff. Maps to Glyphs. And then that F comes from F. Here we go. Yeah, F comes from F. So we know that should be U. So we can say actually F should be U. Lenses help me filling it in for me. So again, we run this, getting closer. These are not thought to be serious attempts. Getting closer to English all the time. So we can start mapping some of these. AIE, that's probably ARE. So I is mapped to I. So we can say, well, actually, no, I should be mapped to R. Run this again. These are IOT. It's obviously not that. M is mapped to I. That should actually be mapped to N. And, just going through, reading it, slowly getting closer. These are not thought to pet serious attempts. So PE, that should be B, isn't it? These are not thought to be serious attempts. So I can go through, well, PE, whatever's mapped to P is Y, that should be B. So I go Y should be B. But again, think about the frequency analysis that blew Hiltrop G's mind. It guessed that Y was P, and the next letter was B. So it's always very, very close. It's not like when it gets it wrong, it's one that's down this end and one up this end. It's always very close. So, we could almost come up with multiple variations where it just kind of tries 2 or 3 different combinations and spits out the results. But, we just keep on doing this. We just keep on cracking it. These are not thought to be serious attempts. So that C is obviously wrong. What maps to, that's probably going to be a P. So this one might actually be a little bit further out because K maps to C, but actually K should be a P, and P's down here. So that was a little bit further. So we're saying K should be P. And then, Cedra, that's got to be secret. That's going to be secret. So what maps to D? X maps to D, and we're saying actually X should be C. So a couple letters away. Sometimes you just need a P. Yes. Yeah. But no, so we just keep going. This is kind of an this is just kind of nice. We're based off knowledge of English. We're guessing. These are not thought to be serious attempts at secret communications. Well, obviously that's going to be an M. So what maps to L? N maps to L. W maps to M. So again, it's close in the frequency. So we're saying actually no, N should be L. Yeah, we'll obviously be a lot more efficient with this. We can maybe set it up so we can, as we go through, we can mark ones as correct rather than constantly go back and getting them wrong. But slowly. These are not serious attempts. I thought N maps to M. That's me putting the L in there. I'm encrypting my own stuff. There we go. There's not thought to be serious attempts at secret communications. Where do we go to next? The earliest, well, that earliest, that's got to be earliest. That's going to have to be earliest. And so, well, what map? O maps to D. We think that should be an L. W maps to L. Again, we're nice and close. It's always within that frequency analysis. And that's kind of the mind-blowing thing of it. It's always inside that frequency analysis. And we just, yeah. And so on and so on and so on and so on. It's, yeah, I'm not going to sit here all day doing them, but I'm just going to copy and paste the rest of the letters because it's not interesting watching me do the same thing again and again and again. But yeah. And there we go. It's just a few more substitutions, and then we've got the earliest known use of cryptography is found in non-standard hieroglyphs carved on the wall of a tomb from the Old Kingdom of Egypt circa 1900 BC. So this is actually an extract from the Wikipedia article on historic cryptography, and we've taken this in an encrypted form and decrypted it just by going through using frequency analysis to work out what letters are there. Yeah, if you had to do this letter by letter, kind of all the different possible substitutions, you know, you'd be there forever. But using frequency analysis allows us to make these smart guesses. And then what's cool is we can then take this mapping that we've got and then apply this to more text. We don't have to keep going through the same process again. Once we've got the mapping, we've got that cipher. We know how to decrypt something else. So if I were to take another block of text, for example, and let's create a new file. We'll call this one here's a new block of text. And what I can do is I can take my mappings. So these mappings here, we worked out some of these. The rest are just the ones based off the frequency. So we only worked out up until J, which is some of them. So we did, how many did we do? We did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, 21. So let's 5 of them just happen to fit in naturally with the right frequency analysis. But yeah, we take those mappings, drop them in here. Put those in here, and then we can take this. I want to fix my Python code. If I now on this and go Python hidden, bang. So it was encrypted is the same substitution key. We've worked out the mappings and we have decrypted it. So in the space of kind of 25 minutes, we have worked out how to crack this code. So anybody who does a message like this is how you can decrypt it. And we decrypted this to say David Kahn notes the code breakers that modern cryptology originated among the Arabs, first people to systematically document cryptanalytic methods. It's all about, again, extract from the same Wikipedia article. But it's really cool. We kind of worked out how we can decrypt this. So now it's no longer safe. You know, I've got my decryption algorithm. I can take anyone's code there. And so as long as we've got enough text, we can use this kind of frequency analysis method using a little bit of Python code. I mean, all in, I've got 136 lines, and that's including all my mappings and the text and frequencies and all that. But using 136 lines of Python code, we've worked out how to decrypt text. And yeah, it's incredible. As mentioned earlier by Hilltribe G, the whole mind-blowing thing that we can literally just take these frequency mappings, use these to make a good guess, and most of the letters came in roughly the right place in the list. You could probably write an automated algorithm to go through and just move each letter kind of 1 or 2 steps up and down the frequency list, run those through a spell checker, and check for the right answer, because the hard part is knowing it's the right answer. I know it's the right answer because I can read the text in English. And that's it. That is ancient classification, or ancient cryptography in Python. Now, if you want to get going with Python, if you're not a Python person, aka.ms/program with Python. We've got the links to be dropped in the chat at some point. This will get you started. It's a whole lot of free videos that teach you Python. Lots of very short videos teach you all about Python. Really cool set of resources. But with that, thank you very much for joining me for this session. As I say, all over the internet, Jim Bob Bennett. Please feel free to get in touch. Got any questions? yeah, I'm here to help. And yeah, if you want to see all the code from today, there was a link in the chat. We'll just get it dropped in again, so you can grab it. Locton says, thanks, Fiona. Thank you very much for joining. I hope this was a bit of fun, just something a little bit different. I'm going to be back next week with another Jim Learn stuff with Python, and I'm going to be looking at PyScript, which is a way of embedding Python inside your web page, just like you do with JavaScript. So that should be fun. So yeah, with that, thank you very much indeed. Alejandro, thank you for joining.
Thank you everyone for joining. I appreciate it. Thanks, Jim, for the really nice session. Before everyone goes, if you have any feedback you'd like to give us, please go to the AKA link I just dropped in the chat and use the code 16299 to do the survey. And other than that, thank you so much for joining. I appreciate it.
Cool. Thank you, everyone. And Marie, thank you for your kind words. I'm glad you enjoyed that. That was a fun session, so glad you enjoyed it. Thanks all.